understand what root multiplicity lets us predict about a graph. I think we all know what root multiplicity is, so we don't need to discuss that. No, that's not true. We have no idea what root multiplicity is. We need to talk about that. Right? So apparently there's this thing called root multiplicity that is going to let us predict or say certain things about what our graph is going to look like. So we need to know what the heck this means. Okay, so let me give you the very non-technical math version of a definition of root multiplicity. Okay? Root multiplicity means how many times does a root occur? Or answering, I guess, question mark, because answering that question. Like if you have a polynomial and you factor it into several factors, if two of the factors are the same, then you're going to get two roots that are the same. And so sometimes you can have a root that occurs more than once, sometimes 2 or 3 times. That is called multiplicity. How many times does a particular root show up as an answer to a polynomial? If it shows up more than one time, apparently slightly unusual things start to happen. Okay? So we'll come back to these things in a second here. Let's start with this. Start with this. In order to understand what's going on here, we're going to let me back up here. Sorry. We're going to factor something that's pretty easy and then graph it, and we'll compare a graph with our results and see if we can learn something. I forgot about this, though. I wanted to show you this. When we did quadratics, we did a whole chapter by factoring and stuff, and then at the end I was like, oh, here's the quadratic equation. You can use this instead for a lot of these things. There is actually a cubic equation. There's a cubic equation as well. So instead of working hard to factor these things, using your graphing calculator, all that kind of stuff, instead, if you want to, only if you want to, you could use this. So, you know, I want to make sure, I want to do what's easiest for you. So if you want to use the cubic equation instead of all this synthetic division and graphing nonsense, there you go. Good. Yeah. See? I just want you to know. Now look at this. Look, there is a binomial being cubed added with a trinomial being squared inside a square root, which is inside a cube root. Yeah, I know. This is not, I just wanted to show you that I'm not showing you like the hard way to do things just to get to the last section and be like, oh, real quick, here's a formula that does. That's not going to happen this chapter because this is not the easy way, obviously. Okay, just thought you'd like to see that. Now, we're going to start with this. We're going to solve, okay? We are actually going to solve and find the roots. We're going to do it by factoring, and then we're going to graph it and compare. So, let's factor away here. You can just divide by the 3. I don't have to actually factor it out because I've got an equation and it says solve. So just divide. And I've got x to the 5th plus 6, x to the 4th plus 27. Bless you. 9, that is, x to the 3rd equals 0. Okay. Now let's factor. GCF is x to the 3rd, so I'll pull x third out. I've got x squared plus 6x plus 9. I told you this was an easy one. What are my factors there? 3 and 3, right? X plus 3, x plus 3. Okay. Now, if I were to write out the roots for this, come on, little board. Are you done with your static thing yet? Yes, you are. Okay. If I were to write out the roots, here's how this would go. Okay. I'll start with these guys. This would give me an answer of minus 3. This would give me an answer of minus 3. X to the 3rd. What would this give me an answer? 0. How many times? 3 times. Because x to the 3rd, that's x times x times x. It's 3 little x factors, and if you set each one equal to 0, you get 0 3 times. And it's unusual to list them out like this, but I'm going to list them out. This adds up to 1, 2, 3, 4, 5 roots, which is how many we need to have anyway because our degree is degree 5. That's how many roots there are for this polynomial. Okay. Graphing calculator time. I want you to go back to the very top before we divided by the 3 and everything. and put this in your graphing calculator, please. And once it's in there, just hit zoom 6, so we're all looking at the same thing. Please. Zoom 6. Great. I'm going to take this and put it on our screen here so we can look at it. Oh, come on. There we go. Let's put this in the background so it can overlap a little. There we go. All right. Odd degree. What kind of shape do odd degree graphs make? No. Like this, right? Not W. Even degree, odd degree. Remember, even, odd. So we're expecting some kind of S shape. And we have that. We've got this weird thing where it kind of comes up here, touches there, and it looks like it goes back down, and this weird thing here. Okay, some kind of S-shaped graph. Now, I also, to get a better view, I want to get a better view of this middle part here for a second. So I'm going to zoom in on this, hit zoom, and then choice 2, you got to hit enter twice. Once to select it, again to actually do the zooming. You should see this. It just kind of focuses in on the middle part of your graph. And it's doing this weird kind of bend thing here. We got to talk about that. So I'm going to put this on our screen as well. Oh, come on. There we go. Okay, here's what I want to observe. First of all, let's take a look at this. 1, 2, 3. This appears to be x equals minus 3, right? And we could check on our graphing calculator to verify that. This is weird. Graph is kind of coming up, it's doing this thing, it's heading back down. What's it doing right here? What's it doing? How would you describe that? Somebody couldn't see this picture. You'd say, well, the graph is coming up, and then what does it do, Jacob? Reaches, and then stops and goes back the other way, right? Now, that's unusual. Usually, when we have a root, we have a point where it crosses. Well, it's not crossing. It's touching. The official math term for this is touchy, no crossy. Touchy, no crossy. No, it's real. Look it up. It's coming up to the x-axis, and it's just hitting it at one point and then going back the other way. Okay? Weird. Now, if we look at -3 in our answers, here's what you'll notice. -3 is an answer that has, and here's how it's said, okay? Multiplicity 2. Multiplicity. Remember, multiplicity means how many times a root gets used? It's a root 2 times. It shows up twice. So -3 is an answer, is a root with multiplicity 2. Okay? And by the way, 0 is a root with multiplicity 3. Now let's look at what it does at 0, because this isn't normal either. It crosses right here. This is at x equals 0. But this is not normal. See, normally when we have a root, the graph just flat out, it just crosses. It just goes through. That's not what it's doing here. How would you describe that? What's it doing? It looks like it's flattening a little bit, almost. It's not actually getting completely flat, but it looks like it's going that way. How else could you describe that? What? Plateaus? Sure. It hesitates, I don't know, bends, plateaus. So that it's doing this weird like little hitch there, right? Okay. Now it's observation time. -3 shows up twice. It does this weird business. 0 shows up 3 times. It does this weird, I mean, it crosses, but it does this weird bend thing here. What's the connection here? What's making it do that? Do you think, Zach, do you think it's about anything special about -3 and 0 as just numbers? Has nothing to do with, there's nothing magical about the points -3 and 0. So what about them? Why is -3 doing the weird touchy, no crossy thing, and why is 0 that occurs 3 times doing the weird bend thing? What's the connection between the two? What do you think?
When it's brought to the power of the number, it does like a U shape, so power of 9 is a U shape.
Huh? That sounds reasonable. What do you think?
Is it because it has to keep one out?
Not exactly. Well, no, not necessarily, because you can get a triple root in other ways. It's more about the triple root than it is anything being on the outside per se. In this case, this is what caused that, right? I think your observation is outstanding. I mean, you guys hear what she said? She said that it's about the power of like 2 times, which is a particular kind of number, an even one, and this is odd. So our tentative observation is that if you have a root that occurs an even number of times, you'll get something like this. And if you have a root that occurs an odd number of times, you'll get something like this. Your book does a very good job of summarizing this. Don't copy this because this is a lot. I just want you to see this, okay? Start right here, okay? The multiplicity of a root is the number of times that the root shows up as a factor. We know that. Here's the deal. When a real root has even multiplicity, it shows up an even number of times, right? And by the way, it has nothing to do with the number being even. Like -3 is an odd number, duh, right? The point is it's used, it shows up twice, which is an even number of times. When that happens, the graph touches the x-axis but does not cross it. That's the observation. That's the observation. On the other hand, if a real root has odd multiplicity, like our 0, where it occurred 3 times, what will happen then? Well, greater than 1. Oh, we'll talk about that in a second. The graph bends. It does that weird, hey, you're supposed to get bigger when I do that. There. It does this weird, like almost flattens out, this sort of hesitation business. That's what it does. Okay? There we go. Now, here's the thing, guys. Wait, what was I going to say? What's my train of thought? Yeah. Greater than 1. Thank you. Why would they have to say that? Because normally what happens is you have a root that just occurs 1 time. And we know what happens when a root occurs 1 time. It just goes straight through. It doesn't do this weird bend thing. Well, 1 is an odd number. And they're just saying, hey, we're not talking about that. If a root occurs an odd number but bigger than 1, like 3 or 5 or 7, if that happens, then it's going to do this weird bend thing. Okay? If you decided not to learn anything else from this whole section, which is a bad plan, don't do that. But if you did that, but yet understood everything on this page, this is like the main thing in the section. This observation, connecting these facts. Okay? Let's do this. Let's make a visual summary. Okay? 3 simple little sketches here. Anywhere in your notes that you want. We're going to do this with an S-shaped curve because I think it's a little easier. And I want you to draw this S-shaped curve, and you can tweak how it looks a little bit, okay? But draw an S-shaped curve through each one of these to demonstrate what each of these 3 scenarios might look like. Okay? Give it a shot. The worst that could ever happen is that you would erase it. Let's try it. with the one that's in my opinion, is a little easier. You might disagree. I don't know. I'm going to start with this guy. Multiplicity is even. Now, I gave you I said to use an S-shaped curve. Okay. Now some of you were like, I'm not going to do that. I'm going to do a W-shaped curve. And you did something like this, where clearly it was touching in two places, and that is even multiplicity. That's fine. But you could draw an S-shaped curve, and you're always going to have one regular root, but then the other one could go like this, right? This guy right here. I know this one just flat out crosses. This would be a regular old root with a multiplicity of 1. But this guy right here, this would be an example of a root with an even multiplicity. It looks like 2. Now, one of the more common mistakes over here is to do this, okay? Is to draw the S-shaped curve and to go like this. And put the bendy thing kind of right here. That doesn't belong here. That belongs. Apparently does belong there because I can't move it. Come on. Is there a lot of static today?
Yeah.
The locker shocked you? Like, been shocked by like opening class doors and stuff? Because this board is just like going crazy. Okay, so I'm going to grab this. It's good to know. This actually, here's how I'm going to fix this, okay? See that? Maybe move it over like this. In order for a root to have a multiplicity of 1, look, I know all these S-curves do a bend thing like this, but the point is that can't occur right where it's crossing. That belongs over in this situation, like this. Okay? And I moved it to the side to show you that there's nothing special about 0, 0. So here's our 3 situations. Situation number 1, your root has a regular old multiplicity of 1. It just crosses, that's it. You have an odd multiplicity, but it's bigger than 1, which means it does this bend, this sort of hesitation in the graph where it crosses. That's critical. And then when the multiplicity is even, you're going to have a root that just touches but doesn't cross. This is the summary. This is the scenario. Okay? We need to check this out and see how this will let us solve stuff. So take your graphing calculator, please. Write this down first, actually, and then take out your calculator. We are asked to identify the roots. That's another word for solve. So we don't have to be careful here. If we see a GCF like a -2, we can just divide everybody by -2 to get rid of it. So we have x to the third plus 6x squared minus 15x minus 100 equals 0. Now that's the thing right there that you're going to put in your graphing calculator. X to the third plus 6x squared minus 15x minus 100. Hit zoom 6. We should all be looking at that. I found if you forget your calculator when you go home, just like sew it to your forehead, and you'll remember it the next day. Yes, it's painful, but you'll remember it. You'll be there. Yep. Okay. Really similar. We are going to get the same answer, but I put the graph in after I divided by -2, and you put it in before. So your graph will be flipped over compared to mine, but we'll get the same results. So you can either change it and do this, or you can keep going with this, and we'll get the same answer. Okay? So let's see what we know. We know lots of stuff, guys, about this. Lots of stuff. 1, 2, 3, 4. This appears to be x equals -5. Appears to be. How many times? just by looking at the reference, do you think that that root occurs? Twice, right? Twice, because it touches, it does the weird touch but doesn't cross thing. So that means it's got to have an even multiplicity. And I'm going to go with 2. Definitely not higher than 2, like 4, because we only have 3 roots to give away here. So this is probably going to be x equals minus 5, comma, multiplicity 2, meaning this root will probably occur twice. Now, we'll check that out in a second just to make sure we're right. But that's what I think. Now, this guy over here, 1, 2, 3, 4. Well, it just straight up crosses, right? It doesn't do the touch but don't cross thing, and it doesn't do the weird, hesitation bend thing. It just crosses. So that's a dead giveaway for x equals 4 with regular old multiplicity of 1. I am highly confident that these are our roots. 2 plus 1 adds up to 3. Nobody's missing. We're good. Now for this one time, because it's the first one we've gone through, I want to do a little synthetic division here. I want to show that we're right. And after that, we can trust that we were right and we don't have to check ourselves every time. But I want to show that we're right. So I'm going to take minus 5. I'm going to put minus 5 in the root box and write the coefficients of this. So 1, 6, minus 15, minus 100. And I'm really, really sure that I'm going to get a 0 remainder because I know minus 5 is a root. So here we go. 1 times 5 is minus 5. Add up for 1. Multiply for minus 5. Add for minus 20. Multiplies for positive 100. Adds for 0, of course. You know what I'm going to do? X squared plus x minus 20. I'm going to take these coefficients. And I'm going to do it one more time. What root am I going to pick now?
4.
I could pick 4. That would absolutely work. But I want to show that I
Negative 5.
Negative 5. How many times, Logan, how many times am I guaranteed that minus 5 will work?
2.
Twice. And I could put 4 in here and that would work, but I want to show that I know what's going on and I want to do negative 5 again.
You forgot the 0.
I forgot the 0 where? Oh, there it is. Okay, thank you. It's like killing you. You're like, you forgot the 0. Oh, okay. So here we go. Put minus 5 in there again because I know it'll work. So 1, this is minus 5, add up for minus 4. 20, there it is. See, look, it works. And look what I'm left with. I'm left with hardly anything. This is 1x minus 4, set it equal to 0, and there's our other. So look, you don't have to go through this every time. I just want you to see that our observations about the graph fit perfectly with all the other stuff we know about factors and roots and stuff. This one is for you. I would divide by 2 and then factor out the GCF of x to the third first if I was you. Yeah. Your calculator has a horrible feature where if you're graphing something and you press enter right in the middle of its graphing, it'll like stop and it'll give you these blinking dots. And it'll pause it.
How did they do that?
Which is great, unless of course you don't know what the heck you've done and why your calculator just froze. You have to hit enter again and it'll keep going. It's minimally useful and it confuses people a lot, so that happens. in a time-saving tip, as you're working your way through this, you'll see the x to the third on the outside, and you'll immediately know, in making your collection of answers, that you've got a root of 0 with multiplicity 3, right? And so then if you were going to go graph the other part in your calculator, you wouldn't include this, because that would make your graph probably more difficult to deal with. You could just include what's left over and work with that. That would be the easiest, smartest way to do that. So you would have x to the third minus 11x squared plus 24x plus 36. And you deal with it that way. What happens when you hit graph? Does your calculator do a good job at this? I don't think so. I think your calculator struggles. It tries hard. Look. Oh, it actually does okay with that. Last period I must have put this in without having taken the x to the third out. I must have put the x to the sixth in there. I think that's what I did. How many people put it in their calculator with x to the sixth? And how many people got the third out and then put this in there? Or about half and half. About half and half. Okay. It's easier if you have an x factor on the outside. Pull that out. You can tell these roots extremely easy. You've got a root of 0 with multiplicity 3, and then you can graph what remains inside. Your calculator does a better job. For those of you who put the x to the 6 version in there, your calculator kind of it looked like it just stopped over here because it got so steep it didn't do a very good job of drawing. So I'm going to go with this version because this is a little easier, okay? I'll give you a second to catch up. Oh, but you do it on the outside and you put times, so it's going to multiply. You really actually did the x to the 6. You get rid of that, and now there's no 6. You should be seeing what I'm saying. There you go. Put this, whoops. Oh. This down here. Who can tell by looking what these roots are? David.
X equals 0, x equals 6, x equals -1.
All right. Now the negative 1, x equals -1, multiplicity, that's pretty clearly 1, right? Because it just goes straight through. What are your thoughts about this one? 2? Because it touches but doesn't cross, so it's got to be even. 2 plus 1 plus 3 is 6. Look at that. We're done. If you had to factor this, guys, if they said, please factor, you have enough from just this information alone to write the rest of the factorization. Look. What? I've got x to the third on the outside. That takes care of these. X minus 1, multiplicity 1, that's this. X minus 1, so that would be this. And x equals 6 with multiplicity 2. That would be x minus 6 times x minus 6. So the roots tell you your factorization. I mean, I like this. I think it's kind of simplified. Okay, real quick. I'm going to do that problem again from 5th period. The problem you just saw was done in 6th period, where I factored out the x to the third, and then I only entered the remaining part of the polynomial in the calculator, which gave you, of course, the same roots, but it made it easier. In 5th period, I didn't do that. I left the x to the third in when I entered the polynomial in the calculator. You get the same roots, of course, but I think it's helpful to see it done this way as well, because it shows you how to handle a common problem with your TI-84 calculator. So the same example that you just saw is going to be done again now, except in a slightly different and more difficult way. And frankly, you shouldn't do it this way if you're really paying attention. But I want you to understand how to handle this deficiency in your calculator. So here you go. I did. Ah, that's what I did. Thank you.
Oh, I did.
I was
do it.
like,
Okay, never mind.
that doesn't look right. Try it again.
Weird.
But I tried it without that. I got it right now. What is this?
For some mathematical cases, that's okay. Let's say you're doing something that's mathematically right. Assume x, right?
I have to show you this text. You're gonna be like, you have issues? ¿Dónde estás? Pulling the look at the top. Oh, that's cute.
Okay. This is important because your graphing calculator, while being very helpful, is not good at certain types of things. The first thing it's not very good at is because your screen, this is not exactly like an HD screen. This is not graphing calculator in 1080p, okay? These pixels are pretty big. And so when you have lines that are very, very steep and very close together, it tends to just decide to like take the rest of the day off when it doesn't know how to draw it any better than what it's done. What's happening here is this, okay? Expand this a little bit. This is clearly an even degree polynomial, degree 6, which as we know means it's going to be some kind of W shape. Now what I think is happening, and we'll verify this in a second, I think the graph is going like this. It's coming down. It's clearly coming up here. And at some point, it's coming back down again. I think, literally, I think that it's touching this point and then turning right back around and going up almost vertically. I mean, that's what I think it's doing. Now, we'll check it in a minute. But it doesn't do a very good job drawing that for us. So here's how we would pursue figuring out what's going on. The first thing we're going to do is take our calculator, and I'm going to zoom in a little because I would like a little bit of a better view of what's going on in here. First of all, look. You see it crossing at -1? That's a root. Do you see it doing the bendy thing here at 0?
Yes.
Okay, so I bet that -1 is going to be occurring once, and 0 is going to be occurring 3 times. Remember, it does that bendy thing if it's an odd multiplicity but more than 1. So that would probably be 3. 1, 2, 3, 4. How many would be left over for this point then? There'd be two more left over, which would make sense. So let's see if that works. Okay? So first thing I'm going to do, I'm going to assume that this right here, this is x equals 1, or minus 1, I'm sorry. So let's say x equals minus 1 with a multiplicity of 1, because it's just crossing through. That looks like what is occurring. If I, let's see, what's the best way to explain this? Let me back up. Let's deal with the triple in the middle. Let's deal with this guy, with the x equals 0, because it did its weird bendy thing in there. And that means it's probably a triple root. How can you tell by looking at this immediately that that's correct? What? X to the third, Mila. X to the third. Kind of related to that, but it's more, what is the GCF here? There's an x to the third, right? You could pull x to the third out and have that's x to the third minus 11x squared plus 24x plus 36. And look, you've got an x to the third out here, so you're going to have a root of 0, and clearly it's going to occur 3 times, which is what the picture tells us. So it is correct to say, guess what? X equals 0 is a root with multiplicity 3, because we can see it as a factor sitting out in front. We can also see it doing the bendy thing here, which tells us that it's got to be triple root. Now, good luck. It is. But the middle one, where it does the bend thing, remember? When does that occur? That only occurs when you have an odd multiplicity bigger than 1, not even. It wouldn't be 6. It could only be 3, 5, 7, etc. That's one. So, now let's see if we can figure out the rest of these. So we've got a triple root here at 0. Let's figure out this guy. It would appear to us, that x equals minus 1, that would be a root with multiplicity of 1, just a regular root where it crosses. So I'm going to actually take minus 1, put it in the root box. I'm not going to worry about this guy up front right now. I'm just going to divide by these guys. I've got 1x to the third, minus 11x squared, 24x, and 36. I'm assuming that I already know that that's going to be the case. So let's see. It's minus 1, adds up for minus 12, multiplies for 12, that's 36. This minus 1 is minus 36. Yes, it works. So I've confirmed at least this much. Now look at what I have left. Constant x squared. This is x squared minus 12x plus 36. Does that factor? It's a quadratic. Oh. Right? So I was correct about this thing coming down and just hitting and then going straight back up, even though your calculator does a terrible job drawing it for you. So sad. This right here, this is x equals 6. It's x equals 6. Multiplicity 2. 2 plus 1 plus 3 does add up to your total. So you've used all the stuff that we know, using your calculator, the greatest common factor, observations from the graph, to figure this stuff out. I like this. I think this is interesting.